So very good evening to everyone. First of all, I would like to thank IPTA for giving us an opportunity to be a part of this knowledge sharing session. I come from a company called Solvina. It's a Swedish-based engineering company, and we have been working a lot on improving the reliability and energy efficiency of the systems. And since morning, I have learned a lot. Yeah. Right, so since morning I have learned a lot about how to improve the energy efficiency, increase the productivity, and heard a lot about some big words like artificial intelligence, machine learning models, and so on. But a few things in the plant which can be solved with some very basic engineering problems are there. And we haven't talked about reliability, which is a very important or critical thing for especially the plant owners when you face a lot of blackouts or trippings in the plant and you get sleepless nights. So that is what we would like to focus upon. I have two case studies to present and I will go one by one. Just to give you one instance that when we talk about reliability, there was an instance, if you recall, in 2012, July 30 and 31st, there was a severe northern grid failure happened. The whole grid collapsed and you can imagine the losses that we faced. So most of the islanding schemes, most of the load shedding schemes, they are prepared on papers through some simulations or through some history of the data, but they are never getting validated. How do you validate that? How do you make sure that it will work when the real situation the plant will face? So these are some of the challenges that we mostly address. So without ado, let's go through. Its first case study is about the Reliance, and the challenge was they were replacing their gas turbines and they are coming up with CFBC boilers. Obviously, cost is the reason, but the challenge is how they will handle the dynamic situations in the plant to supply the steam and power to their petrochemical units, consumer units, because GTs were very fast in response and CFBC boilers are very slow in response, having around 10 to 12 minutes of response time. So once this new plant gets commissioned, and how they will survive the contingency situations, let's say they go into an island, some grid fluctuation happened, and whether they will be able to survive or not. So that was some of their questions. And other questions was, what if my one boiler is under maintenance and another one gets stripped? What if my one turbine gets stripped? How I will handle all these contingency situations? So we did our detailed studies of their system, including integrated steam and power studies for different contingency scenarios, like when the whole system is grid connected and when the whole system is getting islanded from the grid, and there were several contingency situations I'll show you. And as a result of it, they get a very fast transition to the new system. The commissioning time was quite less, and their control systems were so well prepared to handle any of the contingency situations. So we studied their fuel systems, steam systems, boiler feed water systems, electrical, and basically the controllers behind the process side as well as on the electrical side before commissioning, and we verified that their control functions to work. We developed some new logics for them to run the plant in a complete auto mode. We tuned their PID parameters for normal as well as during contingency situations, so that the load shedding should be kept minimum, so that the plant parameters are kept within an acceptance criteria, especially the main steam header pressures. And the frequency in an islanded mode should remain within the protection limits. This was their existing plant configuration where they had these GTs and HRSGs. Their HP header was 115 bar. The flow rate varies from 500 to 900 TPH, and they replaced with 5 new CFBC boilers of 500 TPH each. and 4 new turbines of 93 megawatt each. Now, how we do it? So our basic methodology is that we develop a complete dynamic model of entire plant, including the boilers, turbines, the entire steam distribution network, as well as the entire electrical control system network, along with all the consumer units like PTA 1, 2, 3, and cracker units. So once we have a dynamic model of the plant which closely replicates how your real system would be, then we start with the sensitivity studies where we start giving the load steps to the system. And we start with the smaller steps and we gradually increase the load steps to see up to what load handling limits the system will survive and up to what limit the system will not survive or it will fail the acceptance criteria. So in this case, we started with a load step of 30 megawatt. We gradually increased it to 70, up to 70 megawatt, and we have seen how the steam flow will change. So the steam header flows, if you see here, the purple trend, which is of 70 megawatt, is something worth to see here because it is the largest load step, and obviously initially it will have a dip and then it stabilizes because the boiler takes times to ramp up to deliver that amount of steam. So it roughly takes about 60 minutes to stabilize the header pressure. Then we see how the header pressure gets stabilized. Obviously there is a largest dip for the 70 megawatt load steps. And this is how the boiler demand signal is performing. So for 70 megawatt load steps, as you can see here, my boiler is almost going from 84% to 100%. So they are getting saturated at that level. So the maximum load swing the plant can handle is up to 70 megawatt. So this is what it answers, that how you find your operational limits. And within that operational limits, how you prepare your operational strategies, that is what we have suggested. And we also seen how the STG response are, which are quite fast in action, 60 seconds, they are getting stabilized. The frequency in an islanded mode for each load step, it is well within their protection limits or allowable limits. The consumer battery limits, it is also quite important to see this parameter because for 70 megawatt load step, the purple trend, if you see, their PTA 3 plant will trip if the pressure goes below this acceptable range. So we cannot go below this step, or the plant cannot survive in this condition, otherwise PTA 3 will get tripped. And let's see a case, then we run a simulation cases before we do this sensitivity study to identify all the operating ranges of the plant. Then we study the anticipated scenarios that could come up in the plant. So for this particular case, we have seen trip of one boiler while another was under maintenance, and in both the cases when the plant is grid connected as well as islanded. So on the left hand side is the grid connected graphs, and on the right hand side is the islanded. So when the system is grid connected, as soon as the another boiler is getting tripped, my steam generation and consumption goes down because my turbine has to ramp down. But here we have the maneuverability to import the power from the grid because the system is grid connected, so it is quite easy to handle. But when the system is islanded, when we don't have maneuverability to import the power, there we have suggested that you already have one HRSG in place. So keep that HRSG in hot standby condition at 60 TPH from the start. And as soon as the another boiler gets tripped, ramp it up to 110 megawatt, 10 TPH, so that you compensate for that deficiency in the steam that arises in this particular scenario. And we also see the responses of CFBC boilers, especially because this is their worst case scenario, because the boilers are almost getting saturated in this case when they ramp up to their maximum limit. So that was their one challenge, that how the boiler ramp rates can accurately be analyzed. So we developed a detailed model of the boilers, including superheaters, economizer, air preheaters. Around 3,500 variables are there being modeled in that. And when we we have simulated the whole scenarios, we come up with these results which answers that how my steam output will behave as the load is increased, how the steam outlet temperature will be as the load is increased, flue gas temperature, and so on. So one major achievement from this particular project was the boiler ramp rates were very well improved. It has come down from 12 minutes to 6 minutes. So boilers were pretty well tuned, the logics were working perfectly fine, their PID parameters were tuned. Some master header controllers has been deployed there, and this is the feedback that we got. I don't know, it is visible that their plant is running from last 5 years without a single trip. Another case I wanted to show you is for a pulp mill, Iggesund. It's a part of Holmen Group, a leading pulp and paper company in Sweden. So we have been working with this customer from last 24 years. So their challenge was they were again getting into one new recovery boiler and one new turbine in their existing system. So they asked us to do the simulation studies for their steam distribution control and design the philosophy for all these contingency situations. So as a result, there was a smooth startup, no controller, no system tuning or reworking is required. So for this particular case, it's a fully integrated pulp and paper mill, around 330 tons of capacity, 150 TPH boiler and 50 megawatt turbine. This was their design requirement that they want to run their plant in completely auto mode, compensate for all manual operations. For all turbine control modes like back pressure, frequency or power, there were 35 valves along with the PRDS system and a steam accumulator in the system. So we developed a very simple control strategy for them. So for each steam header, there were 6 steam headers. So for each steam header, we designed separate PI controllers. And we achieved the pressure stability within 1 to 3%. And the system can handle large load swings like turbine trip or board machine start or stop. And we also use this smart split range control strategy where we have prioritized the control valves operation in the sense that we reduce the steam venting. We can utilize the steam as much as possible. So the highest priority was given to the highest steam header, which is of 110 bar, then 60 bar, 65 bar, and come down to 3 bar. So that all these valves open in a certain sequential way so that steam can be better utilized up to down to the process and maximum being utilized within the process without getting wasted. So this is smart split connections, they handle the immediate actions. Also in the case when there is a turbine trip, so immediately this control system decouples and manual actions and limitations can then be taken care of. And once we did this study, we have validated these simulation results with the actual test on site. So that is where we have our testing kit through which we test this system and its performance. So I just wanted to show you, normally the power plant with turbine generator system is connected to the main grid and the governor senses the real frequency, and based on the changes in the real frequency, the governor responds to change in the megawatt output. This is the normal operation. But when the plant goes into an islanded situation, so how we test it is we replace the real frequency with the simulated frequency with our testing kit. So we inject the simulated frequency through the testing kit by which we connect the governor, and then we give the load steps. As in case in an islanded system when some of the loads are getting disconnected or some of the loads are getting connected. So we discuss all those scenarios which come up in the plant and we see. So here in this particular case, when we started the test, there were a lot of oscillations in the output power and grid frequency. Then we tuned the governor PID parameters using Ziegner-Nichols method, and we have achieved the stable operation with tuned parameters. Let's see one of the graph of the test that we have carried out there. So the green trend which you see here is the simulated frequency. So initially the turbine was running at 50 megawatt. We have given a load step of 6 megawatt with a connection of 6 megawatt. So immediately the simulated frequency gone down and the turbine controller has given its output to increase the actual power of the machine. So once the actual power of the machine is increased, the islanded frequency is getting stabilized. So this is what we make sure, that in an island, the frequency is getting stabilized, even with the connection and disconnection of the loads, and how much load swing the system can handle. So for this case, connection of 6 megawatt as well as disconnection of 6 megawatt is quite possible, and the system is getting stabilized. And beyond that, the system could not handle. So even if the machine is running at 50 megawatt at its maximum continuous rating, it can handle up to plus minus 6 megawatt of load swing when it will go into an island. And that is what it gives confidence to the operators. When really they will face this type of situation, they will be able to manage it. Some of the benefits or results that we have seen here is the boiler pressure initially was oscillating around 55 to 57 bar. And after the control was redesigned, it was quite stable around 57 bar. So it's a robust control with steam pressure stabilized, stable island operation, and the energy savings of around 10% that we have been able to achieve here with less venting of the steam. And if we quantify it, it roughly turns around to be around $2 to $6 million annually savings, depending upon the source or type of the fuel. And the payback period for this project was less than 6 months. So thank you so much. I think so yeah, that is it.